Modern software engineering is rapidly converging on a concept known as vibe coding, a continuous, automated workflow that takes a raw idea through analysis, design, testing, and deployment. But as generated code expands outward, the process breaks down. The outputs become chaotic and difficult to manage, threatening the entire system's stability. The core bottleneck here is not the AI's ability to write syntax. Large language models are highly capable of generating code. Where they fail is in managing context over long, multi-step operations. Historically, developers have tried to bridge this gap by relying on external command line interfaces to prompt the agent. Every time a new CLI command is executed, the agent's context window resets, often dropping critical project history. The result is a scattered trail of disconnected Markdown files. The original intent of the human developer is often lost or fractured from the actual execution path of the AI. Maintaining the state required for long-running autonomous tasks depends on a standardized structural foundation. Without it, agent execution becomes increasingly difficult to sustain as project complexity grows. CodyMaster addresses this exact failure point by natively integrating the Fission AI OpenSpec standard directly into the core of its workflow. OpenSpec functions as a rigid spatial map, defining specific coordinates for every piece of project data, rather than relying on loose documentation. By forcing the AI to auto-generate a specific directory path for every new feature, the system eliminates the need for a human to manually organize files or repeatedly feed the agent context. This diagram shows the transition from a scattered state to a localized structure. Instead of isolated data points floating in a project root, every asset is pulled into an organized hierarchy labeled OpenSpec/changes. This centralized directory structure bridges the input-output gap between human and machine. It acts as the foundational substrate required to run a closed-loop autonomous pipeline. To understand how this architecture operates, we must look at the first step of the process, the initialization phase. The system begins with the CM start skill. This internal operation removes reliance on external command line tools to begin a project. Instead, CM start autonomously spins up the standardized OpenSpec root directory for any new feature. This initial creation step establishes a predictable path for context retrieval. The LLM can consistently locate the necessary data for the duration of the build. Once the space exists, the system executes the analytical handoff, utilizing the CM brainstorm idea skill. Here, the AI applies the TRIZ strategic analysis framework to convert raw brainstorming into a structured technical proposal. If we look at the resulting proposal document, we can see an exact structural bifurcation. The file is split into two distinct structured blocks, one defining the feature's necessity and another defining the proposed protocol to build it. These initialization steps ensure that the AI begins its coding workflow equipped with a constrained, logically derived blueprint. The blueprint is then passed into a translation layer handled by the CM planning skill. First, the planning skill generates a design.md file. This document is created to exclusively house the technical architecture and data flow requirements. This is a deliberate state bifurcation. The system separates the static technical design of the feature from the dynamic task execution required to build it. To handle that dynamic execution, the system simultaneously generates tasks.md, which functions as a specific, verifiable, human-readable checklist. Legacy implementation plans often rely on sprawling paragraphs. This strict checklist methodology forces the AI to break the build into granular, binary steps. This flowchart illustrates the precise flow of data. The processing node extracts the strategic intent from the proposal and routes it into two separate specialized files. This bifurcation enables human oversight within an autonomous loop. It creates parallel interfaces, one optimized for the machine's technical logic and one optimized for human review. With the planning state divided and locked, the system engages its final operational layer, the CM execution skill. This is the precise moment where a fully closed, highly automated execution loop begins forcefully locking into action. This operational phase is defined as Autonomous RARV mode, which stands for Read, Analyze, Refine, and Verify. The execution agent now pulls its working context exclusively from the parameters inside the design.md file and the task checklist. At this stage, the execution system is strictly walled off. is prevented from gathering outside, unstructured data that could lead to logic drift. The AI enters an iterative loop, writing code based entirely on the constrained spec parameters it generated during the planning phase. Autonomous RARV aligns execution with the initial design by restricting the agent's operational environment to the open-spec directory structure. This architecture addresses a core tension. How can an AI update a complex, rapidly changing state without losing human readability? The solution relies on a hidden, machine-readable element, the cmtasks.json file. This split-screen view shows the parallel relationship. On the left, raw JSON syntax. On the right, the Markdown document. When the machine updates a task to complete in the JSON, a corresponding checkbox instantly ticks inside the Markdown file. In this sync process, the AI only interacts with the JSON file to manage its internal state, never parsing the human-readable formatting. A rhythmic data pulse flows from the JSON backend to the Markdown frontend, keeping the interface continuously updated. This dual-state synchronization achieves machine autonomy while preserving transparent, real-time human oversight. As the execution loop nears the end of its checklist, it enters the final verification phase of the RARV process. The AI autonomously audits the finished code against the original strategic rules it defined in the proposal.md document. Once the JSON sync confirms that all array tasks are complete and verified, a cleanup protocol is triggered. The system automatically moves the entire completed feature directory out of the active working space and into the openspec/changes/archive folder. This migration creates a permanent, immutable historical record of the context and implementation behind the code. Through this strict lifecycle, CodyMaster operates as a stateful engineering agent, capable of retrieving and acting upon a complete record of the project's evolution. Zooming out from a single feature to a macro-level view reveals the impact of this strict lifecycle on large-scale project topology. This visually represents the immense stability of a large-scale system, a place where every individual component follows a synchronized, predictable logic. By utilizing real-time dual-state synchronization, the system maintains context during highly complex, multi-layered builds. Because every action is archived in a standardized directory, new agents and human developers alike inherit a clean, structurally sound project history. By enforcing a rigid, file-driven structure, the Fission AI architecture provides the structural reliability required for high-frequency, advanced vibe coding workflows.